Okay, so I'm having how many vertices? I have V1, V2, V3, V4, and V5. So I have my A, B, C, D, E, F, H. Don't be that neat, okay? So you have these vertices along with its edge information. Okay, so now that I have got this, let this be called as my graph G. I need to draw my incidence matrix B of G, which can be written as I have how many circuits can be formed, how many circuits can be formed. That will be coming on my left hand side. Okay, and for my column, I'll have my edges. I'll call that as A, B, C, D, E, F, G, and H. Okay, so I can start drawing. Now I can see that this is one circuit. I can call this as one circuit, so I'll call it as B1. So which is the edge which is involved? Only G is said to be involved, so rest all is going to be zeros. Okay, okay. So that was one thing that was there. Now next I can see that this is again a circuit. Okay, I can call this as the second one. So I can say I have B2, which consists of the edges A, H, and C. So I have A, C, and H. So remaining area I'm going to fill it with zeros. Okay, now I can have this as another circuit which is said to be called as 3. I can have B3, which consists of D, E, and H. So these are the edges which are said to be involved in that particular circuit. Then I can have this particular also that I can call it as B4, which consists of only E and F. Okay, so remaining portions are going to be 0. Then I can have this whole as one circuit, which I can call it as 5, isn't it? This is 4, this is the whole thing as 5. So I can say B5 consists of A, it consists of C, it consists of D, it consists of E. So remaining portions I can put it as 0. And then you can have like this also, isn't it? Including this F. Instead of E, we'll take the parallel edge, that is F. So I can say that B6 is actually A, C, instead of, then I'll have F. I also have my D. I do not have my E. That's only difference. So this is, do we have any more circuits in this? Do we have any more circuits in this? I don't see any more circuits. So you can see that my B of G, my circuit graph, it actually consists of how many circuits? It consists of 6 circuits. Now looking at each of my row, each circuit of mine, I see that B1, it is only consisting of a single one. So that means it is said to be called as, it is called as a self loop, isn't it? It is having only one vertex in only one edge incident on it. So it is said to be called as a self loop. Now, if you see in my B2 circuit, I'm involving 3 of them. I'm having 3 ones. That means it is going to be what kind? It is going to be my triangular circuit. Now, if I look into this, here also I have 3 ones. Again, it is of the shape triangle. Here also we have 2. So it is said to be actually your parallel edge. Okay, this is going to be a parallel edge. Then B5, it is said to consist of 4 of them. So something like a quadruple, isn't it? Like we had like here. If you see here, we had A, we had C, we had D, and we had F. We also had a circuit that is called as B6, where we are having A, this having C, we are having D, and instead of F, I can use a parallel edge which is said to be E. That is what my B5 and B6 denote. Okay, now if you look into the edge B, if you look into the edge B, what do you see? It is all zeros. It is all zeros, isn't it? It is not a part of any of these circuit. This edge B is not a part of my any circuit. Even though B is there in my circuit, okay, in my circuit matrix, I won't be able to draw it in my graph. I won't be knowing that B is connecting which all edges because that information is not there. I know I have a edge B, but I do not know to whom it is connecting, to whom it is a part of. Okay, so that is the issue with this. That is why we say that we can only reconstruct the graph partially if we are given the graph, if we are given the matrix B of G. the circuit matrix B of G, if it is given to us, we won't be able to draw the whole graph because such edges, which are said to be called as the pendant edges, I won't be able to know what are the endpoints of B because that information is not there in my graph, not there in my matrix. Next, we are going to study adjacency matrix. Next, we are going to look into adjacency matrix. Adjacency, from the very term adjacency, you should understand. See, whenever you study, you should have some kind of connectivity with each term. When we say incidence paranya incident that edge is incident on a vertex. When I say circuit paranya, it is like some kind of a circuit is being formed. So that means you are involving edges that form a part of your circuit. When we say adjacent means I am sitting adjacent to Aparna. Okay, so adjacent is that. So we are going to talk about adjacency matrix, where if we have G as a graph, okay, and it consists of n vertices and e edges, the adjacency matrix is denoted by capital X. Okay, it is said to be denoted by capital X of G. It is wrong. It is said to be capital X of G. And it is said to be a square matrix. It is said to be a square matrix which is of order n by n. Very, very important. You have X of G and this is said to be of order n by n. You know what your n is. It is said to be the number of vertices. Now from this itself you can understand, that when you draw when you're drawing the matrix, what do you have? You have your rows as your vertices V1, V2, V3, and your columns are said to be also V1, V2, and V3. Okay, that is what is there. Now looking into this, what are the elements here? The elements can have a value 1 or 0. The elements can have a value 1 or 0. Now, as the number of rows and number of columns are said to be same, we can call it as a square matrix. Okay, and what about the elements of your matrix? The elements can have a value 1 or 0. What does it mean? If you have a particular vertex, okay, V1, if it is incident on this particular vertex, then you will have a 1. Okay, or else it is going to be 0. We'll see an example for that and you'll understand. Now, it is also called as a binary matrix and it is said to be symmetric in nature. It is used as an alternative to incidence matrix. So, and it is also known as connection matrix. Connection matrix because it tells us the connection between the two vertices. It tells us the connection that is existing between the two vertices. And from the adjacency matrix, we can construct the entire geometric graph that is given. The adjacency matrix, it is very easy for drawing your graph. Okay, it is a specialty. Now talking about the properties of adjacency matrix, each row of your matrix is said to be corresponding to your vertices. Okay, the number of ones in your row will indicate the degree of the vertex. If a row is got full zeros, it is, what does it mean? If you have all zeros here, that means that particular vertex is not connected to any other vertex. That means it is said to be an isolated. It is said to be. It indicates an you can't call it as isolated edge. It's said to be. It is called as a. It is called as an isolated vertex. Okay, it is said to be called as an isolated vertex. The number of ones in the column will again indicate the degree of that vertex, isn't it? So if you have the number of ones, okay, so that will tell me that, okay, this vertex is connected to so many vertices. So that is the degree of my vertex. A column with full zeros, it will indicate an isolated vertex. You have parallel edges and they cannot be indicated because if I have V1 and V2, I have V1 and V2. So if I have a connection between V1 and V2, I'll just draw ones. Maybe V1 and I have V2 here and there are said to be two edges, that is E1 and E2. I won't be able to show us two different values. I'll be only able to show one value. That is, you have a connection between V1 and V2, but we do not know if there are parallel edges between V1 and V2. That cannot be indicated. And for checking the self-loop condition, you have to check the diagonal elements. Now, if you have a diagonal element condition, that is, you can say V1, V2, and V3. You can have V1, V2, and V3. If there is something like this, okay. So if there is a 1 here, these are the diagonal element. These are the diagonal elements. So I see a 1 here. That means I have a connection between V2 and V2. What do you mean by V2 and V2? V2 is connected to itself. That's it. So that indicates your self loop. So this again, if I have a 1 between V1 and V1, it means I have a self loop between V1. Now it says that if G is disconnected graph, what do you mean by disconnected graph? That is, you have different components in your graph which can be named as G1 and G2, which can be named as G1 and G2. Okay, then how can you represent your disconnected graph? Then you can represent your disconnected graph as, it will consist of what? It will consist of x of G1, okay, and x of G2. Okay, just like the previous that we had studied. Okay, this will be the disconnected, if G is a disconnected graph with two components, if G is said to consist of two components G1 and G2, you can say that disconnected graph can be represented in this particular way. Okay. And what is x of G1 and what is x of G2? X of G1 is said to be the adjacency matrix of G1, and x of G2 is said to be called as the adjacency matrix of G2. I'm not repeating all of this because in incidence matrix we had studied the concept of this, so there is no point in repeating it. And this point also we had studied in the incidence matrix, that is, permutation of any two rows or columns simply correspond to relabeling of vertices of the same graph. So if you have your matrix that you have V1, V2, V3 and V4, if I am going to permute this, that I am going to exchange the position of this, that is, if I put here as V2 and here as V1, it is just simply like relabeling the vertices of the same graph. So it is like they are isomorphic. We had studied this in incidence graph. Now we'll see, look into the examples. Simple example for this. Say we have V1, we have V2, we have V3 and we have V4. These edges are called as A, D, B and C. You can have your adjacency matrix as x of G. Please remember the representation x of G. That will be equal to, it will have the vertices V1, V2, V3 and V4. Again you have V1, V2, V3 and V4. Okay, I hope you have seen the vertices and the rows and the columns. So V1 is incident to V2 and V3. This is incident to V2 and V3. I wrote about V1. What about V2? V2 is connected to V1 and V3. V1 and V3. What about V3? V3 is connected to V1, V2 and V4. So it is connected to V1, V2 and V4. What about V4? V4 is connected only to V3. It is connected only to V3. So that is how I can draw the, or you can say I can write my adjacency matrix. This is said to be my adjacency matrix. Now, as we have said, V1 is said to be connected. V1 is said to be connected to V2 and V3. So this is actually 1. Now, looking in this, the row wise itself, if you see, you can see that V1 is said to be connected to how many vertices? It is said to be connected to 2 vertices. So obviously the degree is said to be how much? It is said to be 2. Here also it is said to be 2. So V2 has a degree of 2. And what about V3? It has got 3, 1. So that shows the degree as 3. What about V4? It is connected to only one vertex. So it has got the degree of 1. Okay. So that is what is your adjacency matrix is.